chapter 14 for AP Chem review on chemical equilibrium. First off, defining what equilibrium is. It's a state of no observable change as time goes by. Several different types of equilibrium. The first one can be chemical, so within a chemical equation at some point there's a balance between reactants and products. Physical can be a state of matter possibility. Homogeneous is when the things involved have the same state of matter. Heterogeneous is when there's a different state of matter. One thing to keep in mind when we're doing the calculations here is solids and liquids do not have a concentration involved in a heterogeneous, so we ignore their concentration. Even liquid water, you could actually figure out liquid water's concentration in such a large number like 55 molar, where we just don't plug it into the equation. If I give you the generic equation of, once again, AB equals CD, notice the double arrow showing that reactants and products are constantly reforming each other but are stabling off at the rate at which they do it. This would be how to solve the equilibrium constant. We'd take the product concentration raised to their stoichiometric coefficient divided by the reactant concentration raised to their stoichiometric coefficient. This will work for concentration or pressures. So you might see a Kc for an equilibrium constant for concentration, or a Kp, an equilibrium concentration for pressure. Again, the Kp would only be valid for gases, though, at equilibrium. To figure out if a reaction is product favored or reactant favored, if the K value is greater than 1, it's going to be product favored. If the K value is less than 1, it's going to be reactant favored, which should make sense to you. If you start off with products divided by reactants, if there's more products than reactants, K value is going to be greater than 1. More products than reactants means I'm forming more products than I did of reactants. The next slide is going over the conversion between the pressure and the gas one. So here's Kp for pressure, here's Kc for the concentration, and 0.0821 is my R value times T, again that's the R value without joules, delta N. Delta N is the product number of gas moles subtracted from the reactant number of gas moles. So if there are solids or anything else involved, you don't take into account those number of moles when we're talking about the change in moles, which again, delta stands for change and for moles in this case. When describing multiple equilibrium, what we can do is say we have two equations. A plus B yields C and D, but then those reactants can make C plus D, making E plus F. Overall, the equation would be A plus B equals EF, because these two are intermediates. So what we can say is, if our first equation right here is K1 and here is K2, then my K overall would be multiplying the two equilibrium constants. And there's problems where if we multiplied it by 2, would we square one or the other? Or if it was a reverse reaction, it's 1 over, things of that nature, which is what we'll talk about right here. If I have A plus B making C plus D, or if I have 3 times that amount, again, there's K1, there's K2, and here's a K3 version. So what I'm going to do, K3 being the reverse, I'm going to relate all these together. To begin with, K1, if I cube it, it would just be like K2, because notice the coefficient of 3 in front of everything. So then if I took things to the third power, it would be the same as taking K1 to the third power. If I related K1 to K3, notice that K1 and 3 are reverse reactions of one another, so 1 over K1 would equal K3. Could also be expressed as K1 to the negative first, equaling K3. So that's how to relate multiple equations together. The real tricky part of this unit, the major work that you have to do, is within a calculation. We would have to start off by predicting the reaction direction, which is referred to as the reaction quotient, letter Q. It's still products divided by reactants concentration, but it's not at equilibrium. It's initially what are the products divided by reactants concentration. If the Q value is a lot smaller, if it's smaller than K, the system must go from left to right, from reactants to products, to form more products. If the Q value is greater than K, the reaction must go right to left to form more reactants. And if Q equals K, the system is already at equilibrium. Now I understand some students don't like the fact that, what do you mean a reaction is going from right to left? We always refer to in an equilibrium system the left side of the arrow as reactants, the right side as products. That doesn't necessarily mean that the direction of reaction will always go this way. It could actually go instead right to left, which makes it a little unusual to think about, but at the same time equilibrium system is trying to reach that balance between the two. And there's no way to tell that balance if we keep on switching around what we define as reactants and products. So we're going to calculate equilibrium concentrations here. I'm going to warn you that this question is going to take a lot of work. So if you printed out your slides the way that I did, I would start at the top of the page with this calculation and work your entire way down because it fit my entire page as I worked on this. It says here's the concentrations you begin with of H2, I2, and HI in a container. What are the concentrations at equilibrium if the K value is 54.3? So if we start over here on the board, the first thing I like to do is write down what is the reaction. H2 plus I2 makes 2HI. That's what I'm starting off with. By doing that, now I have a 2. That's going to help me out when it comes time to figuring out the Q value and things like that. I'm going to start by figuring out Q. Q would be the HI concentration squared divided by H2 and I2. So let's solve for Q. If I plug in the numbers, I'm going to have 0.0224 squared divided by 0.00623 times 0.00414. When I solve for this, I get a Q value of 19.45. If the Q value, in this case, is less than the K value, the reaction must go left to right. So sometimes I draw an arrow up above to show which direction the reaction is going to go for me then. So this is the direction of the reaction. Step one in this calculation is figure out which way is it going by solving for Q. Now that I know the reaction is going left to right, what we're going to set up is what they refer to as the ICE method. We're going to figure out the initial concentration, the change in concentration, and the concentration at equilibrium. So initially, my H2 is again 0.0063. My I2 is going to be 0.00414. And then my HI is 0.0224. If the reaction is going from the left to the right, the change is going to be a negative X for the H2. The change is going to be a negative X for the I2. The HI is going to gain then, and it's going to gain 2X. So at equilibrium, 0.0063 minus X, 0.00414 minus X, 0.0224 plus 2X is going to be my concentrations. Now what we have to do is solve for X. And that's going to be the next bulk of work. We're actually going to move over to the other board here to show you how to solve for X. K is going to be 54.3. That's going to equal products divided by reactants. So that's going to be 0.0224 minus 2X squared divided by 0.0063 minus X times 0.00414 minus X. We have to figure out how to solve for X in this equation, which is going to mean, okay, multiply here, here. You're going to have to multiply this to both. You're going to have to square the top. Then you're going to have to multiply by 54.3. A lot of work to deal with that. Step number one is multiplying all this out. So I have 54.3 equals, and then I figured out to be 0.000502 plus 0.0448x plus 4x squared. So I just made my value squared and took it all out there. Same way in the bottom here, if I solve for that, I would end up with 2.58 times 10 to the negative fifth plus a negative 0.01037x plus x squared. And once again, that equals 54.3. what I would next do is multiply both sides of my equation by the denominator. That way, I can get 54.3 times all this. I can get rid of my denominator. It's usually a little bit easier to simplify from there. So that step, maybe I'll kind of draw a line separating this all out. I have 54.3x squared plus negative 0.563 x plus 0.00114 equals, and I'm going to continue my equals on the next line below because, again, there's just not a lot of room for this, 0.0000502 plus 0.0448x plus 4x squared. So all of this equals all of that. Next step is get everything on one side of the equation. So if I do that, I'll have 50.3x squared plus a negative 0.518x plus 0.000898, and that equals 0. So again, I added everything from this side of the equation to this side to get everything equal to 0. This next step is using the quadratic formula now. If you don't recall the quadratic formula, it's negative b plus or minus the square root of b squared minus 4ac all divided by 2a. Now the b value is the negative 0.518. The a value is the 50.3. The c value is the 0.000898. So if our next step is to plug into that, negative b would now be 0.518 plus or minus the square root of 0.518 squared minus 4 times a, which is 50.3, times c, which is 0.000898, and I'm going to divide all of that by 2 times 50.3. A lot of work to do, no doubt. What's going to happen is you're going to have two possible answers, because you can have this plus this version divided by that, this minus this version divided by that. So my two answers for x when I first solve for it are either 0.0022 or 0.0081. Now, if we go back to the other side of the board here for a second, since there's two possible answers for x, I can plug both of them in and see what happens. If I plug in 0.0081 into here, 0.0063 minus 0.0081 would give me a negative value. You cannot have a negative concentration, so that number cannot be correct. So my x value is going to be 0.0022. The question is asking for, what are the concentrations at equilibrium? So to figure out the concentrations at equilibrium, plug x in. So now I can see that if I plug x into here, my concentration of H2 at equilibrium would be 0.00403. And I'll actually just write that on the top here so it's a little bit easier for you to see the final answer. So if I take this and solve for at equilibrium, I'm going to have 0.00403 for my H2 concentration. My I2 concentration, plugging 0.0022 into that equation, is going to end up giving me 0.00194. And finally, my HI concentration is going to give me 0.018. We are going to have to do this one more time in the acid-base unit when we're dealing with strength of weak acids, but for now, all of this work is to figure that out. So once again, to review, first I found the Q to determine the direction of the reaction. So that was prox divided by reactants initially to determine the reaction was going left to right. Then I used the ICE method, initial change equilibrium, to figure out what x was going to be. I had to then use the quadratic formula, and then only one value made sense, and that was the value that I plugged into x to solve for this big equation. So a lot of work to figure out what is the concentration at equilibrium. Next thing we're going to go over is Le Chatelier's principle. Le Chatelier's principle is if an external stress is applied to a system at equilibrium, the system will adjust in such a way that the stress is partially offset as the system reaches a new equilibrium position. Now there's several different stresses that is referred to when we talk about this. So we're going to give you the example N2 plus 3H2 makes 2NH3. And once again, double arrow showing it's an equilibrium expression. First off, we could change the concentration. So for example, if we added more N2 to this equation, we're no longer at equilibrium. We disturbed equilibrium because it's no longer at that balance that it was. If you add more of one thing, the equilibrium is going to shift in the opposite direction. So what we would say is that equilibrium is shifting left to right, or towards the products. So once again, a change in concentration, whatever you add, equilibrium is going to shift in the other direction. Changes in volume, often we refer to changes in volume the same as changes in pressure. If you increase the pressure, so if you push on something more, you're decreasing the volume. A decrease in volume would favor fewer gas molecules. So if you look at this expression up here, if we increase the pressure, we have 1, 2, 3, 4 gas molecules on this side, 2 gas molecules on this side. So in other words, an increase in pressure or decrease in volume would favor the products in this case. If I did the exact opposite version, a decrease in pressure would mean an increase in volume. That would favor the more molecules of gas instead. The very last one to mention is the change in temperature. I'm going to give you an example of N2O4 gas making 2NO2 gas. This is endothermic. Now, if it's endothermic, that means you can treat heat as a reactant. So, if you add more heat to something that's already endothermic, it's like adding more of the reactant, which will make it shift left to right. So there's no easy way to say left or right when we're dealing with change in temperature, because you have to first figure out, is it endothermic or exothermic? So in this case, endothermic means I could write heat as a reactant right here. And if you add more heat, you're adding more reactant to shift the reaction from the reactants to the products. Last thing to mention here in this chapter is that changing temperature can change equilibrium value as well. It can change concentration, pressure, or volume cannot change that equilibrium value. So only the temperature can actually change the actual K value. The others just shift equilibrium to reestablish that K value. And this has been